Hi, so I'm Tim Stubbs. I'm going to talk about the radio occultation observations of a temporally variable dense lunar ionosphere. This is what we've been doing with LRO using the high-gain antenna right there. So, bit of motivation and background. So, radio occultation experiments are used to investigate electron concentrations in planetary ionospheres with signals in the S and X band range pretty routinely. And so these is pretty handy because you actually also use these bands for communications. So you can sort of do double duty on that front. And so basically the electrons in these ionospheres are a dispersive medium for radio waves, which is why you can use them to infer the electron column concentration between the transmitter and the receiver on Earth in this case. And that gives you also, and that's also referred to as the total electron content. So basically just the column concentration. Okay. So, so far, the measurements have been sort of few and far between and often controversial. And so there is evidence of a far denser lunar ionosphere than expected. So some of the measurements sort of infer sort of hundreds or thousands of electrons per cubic centimeter compared to sort of the less than 1 to about 10-ish at most you'd expect from the ionization of the neutral exosphere on the moon. So really a huge puzzle, so orders of magnitude different. So this dense ionosphere appears to be either localized and or episodic. It doesn't seem to be global or in any sort of steady state. So really quite puzzling. So arguably the best observations we have to date come from JAXA's Kagawa or Selene mission. And they made 16 single spacecraft measurements. So that was about a 4% detection rate of this of an occasional dense ionosphere on the day side at altitudes below 30 kilometers and with solar zenith angles below 60 degrees. So sort of very much a dayside phenomenon. And those measurements were somewhat representative of what had been seen before. So this is an example. This is basically like the average of all the observations they made from Kagawa. So this altitude here on the y-axis, and you've got electron column density on the x-axis, and that's sort of the black line there. And then you've got the electron density here in the dashed line. So that's sort of converting from one to the other. Right. So there were some restrictions to these observations from Kagawa's polar orbit. So basically the measurements tended to be clustered around high latitudes and large solar zenith angles. So the coverage wasn't great in that regard. So on average, the peak concentration was about 300 electrons per cc at around 15 kilometers altitude. And the scale height was about 7 kilometers. And again, that's sort of representative of what was seen before, although some of the Soviet lunar missions actually saw, well above 1,000 electrons per cc. And so most of the proposed mechanisms rely on photoionization or photoemission from solar UV, since it initially at least appeared to be a dayside phenomenon. So basically, we really need far more and much better measurements of the ionosphere to really understand what's going on. So in steps LRO. So I'm going to discuss now the occultations with LRO. So obvious question is, why has LRO only recently started doing these radio occultations? Well, it never intended to do them in the first place. So basically, we were able to adapt the LRO communication system, which has effectively created a new science instrument in flight. So, which is pretty cool, right? I mean, after over a decade at the moon, to create a new science instrument is pretty neat. So the challenge is that because LRO wasn't intended to do that, it's managing to keep that high gain antenna pointed towards the ground station on Earth, so we can actually take these measurements. So pretty much when LRO is sending data back to the Earth, it's sort of sending it back here, and the high gain antenna is able to gimbal itself and point to the Earth without interfering with the rest of the rest of the spacecraft. So the solar panels keep pointing towards the sun, and everything else can be pointing towards the nadir. But when you get sort of close to occultation, sort of where you go ingress into the shadow or sort of behind the moon, the gimbling kind of runs out, and you can't gimbal the antenna any further to point to the Earth. So that kind of is sort of non-ideal. So there are a couple of solutions. Number one is just put up with it. So basically allow the high gain antenna bore sight to be pointed off Earth. So you have this little sort of angle here that you sort of, you don't quite point where you want to. The other solution is to execute a spacecraft slew. So you shift the whole spacecraft, including all the other instruments on board, to point towards Earth to get your measurement done. So the benefits of solution one is that you don't have to have a slew. It's all just software on board. The problem is that the Earth ground station could reach wide angular separation, and this creates problems with side lobes. So you get higher noise, phase perturbations, that kind of stuff. So it's not the greatest measurement, although can still be good. So solution two, so you have the same antenna geometry as the nominal tracking. So it's kind of the spacecraft is used to doing that, but it requires planning, executing slews, and it impacts spacecraft operations. So there's definitely a cost to having to do that. So we do adopt both solutions. So the solution one, where we're pointing slightly off Earth, we do those more frequently because they don't cost us anything. And so for every 5 of those, we do about one of the slewed measurements. And so today, we're going to sort of focus on solution 2 using the spacecraft slews because we have much better data quality. And I just might add at this point that the radio occultation performance has exceeded initial expectations. It's really very impressive results. Okay, so just give you an overview of the event. So, wow, this is really washed out. Okay, believe it or not, there is the lunar orbit there. So we observed each day from the 23rd to the 27th of May, 2022, when the moon was in these positions. So this is like the location of the moon at the first observation each day. So the sun's in that direction. So looking down above the ecliptic, there's the Earth. Here's the magnetosphere, and here's the bow shock. So for these observations, we were always in the solar wind. So sort of comparable plasma conditions. So we were observing at high northern latitudes above the far side of the moon, and we effectively observed a fixed location each day, and that's because of the coarse spatial resolution of this measurement. So basically, in terms of latitude and longitude of where we're actually probing, there's about a 15-degree uncertainty, or sort of smearing, I guess. And we were observing it sort of just under 2-hour intervals, and that's basically driven by the LRO orbit period. Okay, so here's an example from the 23rd of May, 2022, and show some examples here. So we're plotting altitude as a function of total electron content. So just for reference, sort of 10 to the 15 electrons per square meter is about the same as 1,000 electrons per cc. But to go from this, which is sort of very much like the measurement, to this requires some assumptions. So we stick to TEC because it sort of doesn't assume anything. And you might just be able to make out some red lines here, and that sort of is an indication of the uncertainty in the measurements. So we go through and we sort of maybe class them as a detection, yes, a detection, no, or a maybe. So first up, this first case, so we count this as a non-detection. You see there's a bit of a wiggle here. You maybe sort of just cross the uncertainty limits, but this is kind of what you might expect if there's no ionosphere, right? So really no detection. Then the second case is a maybe. You see a bit of a deviation here, but I wouldn't really argue strongly that that's an ionosphere. It could just be fluctuations. Now, this one is a real textbook example of no ionosphere. So, the wiggles barely, reach outside the uncertainties. So pretty much we didn't see an ionosphere here. And then in the final case, you can see that there's no ionosphere. And then as you get lower down, sort of below 30 kilometers, thinking back to what Selene saw, you get this very steady, deviation where you actually get sort of densities increasing as you move close to the surface. So this really looks like a clear detection of the ionosphere. And just for reference, so during this interval, we're at the high polar northern latitudes, sort of above 80 degrees on the far side, really close to the terminator. So just 5 degrees from the terminator, and just in the early morning, at sort of high polar latitudes. Okay, so this gives an overview of the all of the events, and I've sort of gone through giving like the yes, no, and the maybes. And so basically we had 23 observations in total, 9 detections, 11 non-detections, and 3 possibles. So that 9 detections out of 23 is about a 40% detection rate, which is 10 times higher than what Kagawa saw. So that's really quite astonishing. And so if you sort of look at these events, and bearing in mind that they're sort of one after the other, so there's less than a 2-hour gap between each observation. And so this shows that this dense ionosphere can form or disperse in less than 2 hours, sort of a good example here. So there's no ionosphere, it forms, then disappears. And so things appear and disappear on less than 4-hour timescales and do the opposite. So disappear, then reappear on less than 4-hour timescales and possibly persist for more than 2 hours. So there's a lot of variability all on sort of hour timescales, which is very much a new result for the dense ionosphere. Okay, and just to give you a sense of kind of what's going on at the time. So, so these observations were trending northward and westward, and they were all on the day side for these first couple of days, and they were just in sort of the early morning. Then for the last 3 days, things were trending southward, westward, and we're on the night side, but only by within about 5 degrees of the terminator. And so we're just pre-dawn. And like I said, we're only just 5 degrees sort of behind the terminator. So given our uncertainty on location is about 15 degrees, there could be a contribution from the day side here, but it's still an interesting result that we're actually seeing stuff that's supposed to be above the night side, especially if, you know, the processes that form this could be driven by solar UV. Okay, so causes of a dense lunar ionosphere variability. So, Cesare is just talking about the lunar ionosphere. Sorry, oh, okay, yeah. So the classical lunar ionosphere is typically created by photoionization of exospheric neutrals. And so for the exosphere, this is a major loss mechanism. So basically things get ionized, they see the convection electric field in the solar wind, and they get picked up and they get lost. Or they get driven into the surface and recycled. So that's pretty much what we expect to happen. So some known drivers of the lunar exosphere and plasma environment, so things that might be triggering this ionosphere, dense ionosphere, are solar UV. So we know we can get sort of photon sputtering of neutrals and ions from the surface and the exosphere. They also drive photoionization and photoemission. So the solar wind, so space plasmas generally create so ion sputtering, and they have that convection electric field which sort of transports ions away or towards the moon. Then we have energetic particles which can also do sputtering and create extreme charging conditions on the moon. And then finally we have meteoroid impacts which can vaporize the surface and also eject regolith. So so the question is do any of these drivers vary on 2-hour timescales to explain, you know, that could trigger this dense ionosphere that we're seeing? So here are the space environment conditions during these observations, and sort of marked out here is like, you know, vertical lines, you know, well, they are color coded, trust me, between detections, non-detections, and question marks. So at the top here we've got solar UV, and then next down here we're looking at the solar wind. So density, speed, which is also a proxy for energy, flux, the energetic particle fluxes, the B field, which is sort of gives you some context of what's happening in the solar wind. So you've got a co-rotating interaction region here. And then also the E field in the north-south direction. So for our polar location, this is indicating whether ions would be sort of lost to space, so basically, you know, heading northward, or driven back into the moon by heading southward. And it's kind of hard to tell here, but if I go through and I try and look for sort of, you know, consistent trends between seeing and not seeing the lunar ionosphere, there's really nothing, no obvious connection. And I might also mention that this data for the solar wind was taken from the WIND spacecraft and then time shifted to the moon. So we're sort of looking, you know, at the solar wind at the time of the observations. So as I said, no obvious connection between solar UV or solar wind conditions and lunar ionosphere variability. It doesn't necessarily mean that there's not a role that these conditions play, but they don't seem to be triggering this the appearance or disappearance of a dense ionosphere. Also mention, so there were no significant meteoroid streams encountered by the moon during this interval, and so there's no obvious connection with meteoroid streams at this point. And we didn't predict that that we were looking at any sort of substantial magnetic anomalies where we were seeing this dense ionosphere. Because there is some theory that maybe you could get sort of ions trapped in a crustal field, and that might generate this sort of dense ionosphere signal, but there doesn't seem to be an obvious connection. Okay, so summary and future work. So LRO slew to perform radio occultations above the northern polar far side of the moon near the dawn terminator. It was at approximately, the observations were at approximately a fixed location for each sequence. And this dense lunar ionosphere was observed to vary on 2-hour timescales, appearing, disappearing, and reappearing. And another novel observation is we seem to see this dense ionosphere above the night side, but close to the terminator. So there could be a role for solar UV in what we saw. It's sort of up for debate. No obvious connection between the variability of the lunar ionosphere and solar UV, solar wind conditions, meteoroid streams, or crustal fields, magnetic anomalies. So future work, we're continuously working to get more observations to improve our temporal and spatial coverage and sampling statistics. And we're working on developing a phase calibration for the analysis of the off-Earth observations to sort of, tidy up the data for that, sort of for not pointing directly at the ground station. Okay, thank you.
All right, thank you. That was very interesting. Do we have any final questions in the room? No, I think we're good. Okay. Oh, no, we got one in the middle. One in the middle. Nearly missed you.
Hi. So this was very interesting. I was wondering, is it what do you expect in terms of this profile extending all the way to the lunar surface? Like, is it expected, let's say, to connect smoothly with the surface, or could it have some large deviations at small length scales close to the surface? I'm asking because I'm wondering whether it would be interesting to have, as opposed to these orbital measurements, also maybe something ground-based on the moon.
Yeah, no, it'd be terrific to have some ground-based observations. So typically, it's going to take a while to go back, but so some of the observations that we've seen just sort of, they increase sort of monotonically down to the surface. But interestingly, here we go. If you look at the Kagawa sort of average profiles, so this dashed line is the electron concentration density, if you like, and you can see it sort of peaks above the surface. So that, you see that in individual profiles too, that there's a peak at some altitude and then it sort of drops off towards the surface. Yeah.
Right. I was wondering if that possibly that is maybe a coarse sampling, and that maybe there is some smaller length scale behavior that you don't resolve close to the surface potentially.
Yeah, possibly. Yeah. I mean, if we can't resolve it, we don't know one way or the other. But yeah, it'd be neat to get some sort of some helpful observations from the surface too. Yeah.
Right.
Maybe radio or just like an electron spectrometer, just something. Yeah.
Right. Okay. Thank you.